Hello students, in this video we'll discuss the fundamental solution to the one-dimensional heat equation. Let's recall that we're studying the one-dimensional heat equation. We're considering this problem over here, which is ut equals k uxx. U of x0 is some function phi of x, right? And over here, x is a real number, so we have x between negative infinity and infinity. And t is greater than 0, t greater than or equal to 0, right? So this is our heat equation, our initial value problem for the heat equation. Initial value problem for the heat equation. Okay, excellent. And we saw last time, we found phi xc, which was c1 plus c2, the integral from 0 to xc of e to the negative eta squared d eta, solved the heat equation, solves ut equals k uxx, where xc is what? Where xc is just x over the square root of 4kt. These are our self-similar variables, right? So these are self-similar variables. Okay. And so now if we specify a particular initial condition, let me specify an initial condition. So with a special initial condition, Heaviside initial condition, let's specify the initial condition of h of x, which is just going to be 1 if x is greater than 0, and 0 if x is less than 0. Okay? So if I want to find the solution to the heat equation that is of this form and has this initial conditions, we can find C1 and C2, right? So now I can find C1 and C2. Okay? So let's do so. So what's the key feature over here? The key feature over here is that as I let t go to 0, this xc goes to infinity. So as t goes to 0 from the right, xc tends to infinity, right? Okay. So for x greater than 0, we know that 1 is equal to what? 1 is equal to c1 plus c2, the integral from 0 to infinity of just what? Of just e to the negative eta squared d eta, right? Good? And so now what? So now we need to recall something from multivariable calculus. Recall, of course, how do we evaluate these integrals over here? Well, we do the standard trick, right? We say that we let I be the integral from negative infinity to infinity of e to the negative eta squared d eta. Then this implies that I squared is equal to the double integral, negative infinity, of course, of e to the negative eta squared plus eta 1 squared d eta 1, right? And if we change this to polar coordinates, what will happen over here? If we change this to polar coordinates, we're going to have the integral from 0 to 2 pi, the integral from 0 to infinity of e to the negative r squared, r dr d theta, right? So what we're going to have over here is we're going to have that this integral over here, I can actually do this integral. I get a 2 pi from the theta. And then what we have over here, so if there was a 2 over there, that'd be good. So I have a 1/2 e to the negative r squared, right? If I do the derivative of that, I see I exactly get this, right? With a negative sign, of course. Good. And so we validate this from 0 to infinity, right? The top limit gives you nothing, the bottom limit gives you a 1/2, so this becomes pi, right? So in other words, this I is just going to be the square root of pi. So I is the square root of pi. Good. And so therefore, this is, of course, half of that. So when we plug in 1, we get what? We get c1 plus c2, and then that's pi, the square root of pi over 2. Square root of pi over 2. And then similar with x is negative, then you get 0 is equal to c1 plus c2. And then you're integrating from what? Then you're integrating from 0 up to negative infinity now, because when x is negative, that's going to be negative infinity. E to the negative eta squared d eta. And that, of course, is just going to be what? That's just going to be c1 minus root pi over 2 c2. Okay? So now if we add these two equations together, we can conclude that c1 is equal to 1/2. So c1 is equal to 1/2. Good. And then what will c2 be? So c2 then, of course, if you subtract these equations from each other, you get 1 is equal to root pi. So c2 is going to be 1 over the square root of pi. Good. So now I have my particular solution over here, which is great. So now the solution to this solves the problem, and so I can look at this special solution over here and call this function over here phi of x and t, which is 1/2 plus 1 over the square root of pi, the integral from 0 up to x over the square root of 4 kt e to the negative eta squared d eta, right? That's my function phi, and that's a solution to the heat equation with the Heaviside initial data. Now I'm going to define psi of x and t to be d phi dx of x and t, which is going to be, the 1/2 goes away. We're going to have an e, a 1 over 2 square root pi kt e to the negative x squared over the square root over just 4kt, like that, okay? Now this function psi of xt over here, I claim this is the fundamental solution to the Laplace equation, right? This is the fundamental solution. Psi is the fundamental solution. Okay? Now what do I mean by that? I mean the following. I mean, if we look at this integral over here, so if I look at the integral over r of psi of x minus y comma t, and with a function, with an arbitrary function, let's say phi, little phi of y dy, then this function, which is going to call u of x and t, I claim that this solves star. Okay? Now how do I know that? Well, I know, of course, that this is a solution. I know that this function over here will solve the heat equation because I know that if I do a convolution of a solution to the heat equation, I know that phi is a solution to the heat equation. Therefore, psi is a solution because derivatives of solutions to the heat equation are solutions to the heat equation. So psi is a solution to the heat equation. If I convolve a solution to the heat equation with a relatively nice function like phi, I'm assuming that phi maybe has some nice support conditions, then this becomes a solution to the heat equation as well. This solves the heat equation. The only thing to check is when I plug in 0 that we get this phi of x, right? So if I do that, what are we going to get? So I want to show that we actually get phi of 0 over here. So of course, what happens is we can see that this is an approximation to the identity. So if I look at the limit as t approaches 0, right? The limit t approaches 0 of this expression over here, since this function over here is an approximation to the identity, this just becomes phi of x, okay? So we're using the fact over here that this is a very special function. Of course, what we could do is we could formally do this by simply plugging in the derivative of this. We could say that this is really phi x, right? So what we could do is we could say, okay, well, what we'll do is we'll plug in phi x over here, integrate by parts, and then pass to the limit, right? So that's the formal mechanism of solving this problem. We're really leaning to the fact that we know properties of these exponentials, that they sort of peak up like this and form an approximation identity, allowing us to conclude that this function psi is a fundamental solution to the heat equation in 1 dimensions. Thank you very much.